Okay, lesson 1.6 is complex numbers, and I'm going to give you a very quick refresher from Algebra 2 what a complex number is. And so I'm starting out with a simple example of x squared plus 1 equals 0. So of course, if you were to solve that, you would subtract the 1 over. And you would say, okay, I need to square root both sides, and then way back in the day, you would say, wait, I can't square root negative because any number times itself would turn positive. And here's where we define what an imaginary number is. So while x is not a real solution, we can classify it as an imaginary solution. So essentially, the square root of -1 is defined as the letter I, if you recall that. I'm guessing you probably remember that much. Okay, so complex numbers can have a real and an imaginary part, or it may just have one or the other. Okay, so a complex number in standard form, and you're going to want to note standard form is the real and then the imaginary in that specific order. So A is the real part and B is the coefficient of the imaginary part. So for example, this might be 2 plus 3i. That is a complex number because it has real and imaginary parts to it. So really all you're going to be doing with this section, 1.6, is operations. So add, subtract, multiply, divide. Before we do that though, I just want to make sure you understand what standard form is. Okay, so if I asked you to put all of these complex numbers in standard form, that just means get it in the form of a plus bi. So real first, imaginary second. So the first example appears to already be in standard form, but you cannot have one large fraction. So essentially, you're going to separate those two. So 5/3 minus 2i, right? Because 6 divided by 3 is 2, and that's it. Okay, example 2 is good. -3, if you want to write plus 0i, you really don't have to, but that is complex form, real, imaginary. Example 3 only has an imaginary component. If you wanted to write 0 plus, you certainly could. It's not a requirement. Okay, what is the square root of -9? Well, if the square root of -1 is 1i, the square root of -9 is 3i. So this you would just simplify to 3i. Okay, and then same thing, if it's not a perfect square, this would be, so the square root of -3, you can't square root 3, so you bring the I out front and you keep the radical of 3. Okay, so any negative inside a radical is imaginary. And you never, ever, ever leave a square root with a negative number in it. That's improper way. So those are all standard form, real, imaginary. Okay, then you're going to do, like I said, add, subtract, multiply, divide. So I'm going to just kind of remind you quickly because adding, subtracting is so quite simple. It's just combining like terms, your real parts and your imaginary parts. So on example 6, I can, and please do note though, I'm adding, right? So I can add my real parts. 5 plus 8 is 13. Add my imaginary parts. 2 plus -7 is -5. And it's that easy. In standard form, done. Okay, example 7, maybe first the note operation is subtraction, but before I subtract, you probably want to reduce those radicals that have negatives in them. Okay, so let's start there. The square root of 18, 2 times 9, so that's going to be 3 square root 2 with an I. So 3i square root 2. Okay, and then square root of 32. Well, square root of 32 is 16 times 2, so that's going to be 4i square root 2. Now I can subtract, and just be careful with subtraction, right? Again, you're subtracting a negative right there, so be careful. So subtracting my real parts, I have -1 minus 4, which is a -5. Subtract my imaginaries, I have a 3 root 2, and then really plus negative, right? So 3 root 2 plus 4 root 2 is a plus 7i root 2. And there you have it. Okay, so that's adding, subtracting. And of course, multiplication is just like multiplying any other binomial. So I can FOIL, this is a binomial times a binomial, so I'm going to FOIL -2, 10i, inner -3i, outer 15i squared. Okay, now do you remember what I squared is? Ooh, quick, jog your memory. If square root of -1 is I, well, if I square this, I'm going to square this, which means I squared, square cancels out a square root, is just -1. And maybe you recalled that, right? But this highlight is super important. So if I squared is really -1, then this is really -15, right?
Lori Nebeker, please dial 58112.
So combining my like terms,
please dial 58112.
my real part, -2 minus 15 is -17. My imaginary parts, 10 minus 3 is plus 7. And there is my complex number in standard form. Example 9, I really just wanted to point out quickly the radical piece of it is not too terribly difficult. But when you have negative radicals, you should not multiply them, the negatives first, because you're essentially masking the fact that it's imaginary. So for example, with this radical question, I would pull out the I first and make those radicals +5 and +20. So don't take 5 times 20 first, is what I'm getting at. Okay, then you can multiply. So I times I is I squared, and 5 times 20 is 100. And what is I squared? It's really a -1. What is the square root of 100? It's really 10. And this is equivalent then to -10. If I had multiplied these right away, -5 times -20 is 100, and the square root of 100 is 10. You can already see that's different, right? And it's incorrect. So, lesson learned. Don't do that. All right. Then the last operation is division, and I will actually, I'm going to go to that one first. So division, right? Because we did add, subtract, multiply. Now we're going to divide. So when you divide, what it's really going to amount to is rationalizing the denominator. Because remember, I is equivalent to the square root of -1. So if you look at 2i in this question over here, you really have a radical in the denominator, which is not good. So you could change that to the square root of -1 if you really wanted, if that makes you see it easier. Or how do you rationalize a denominator? You multiply by that radical. So in this case, if I multiply the top and the bottom by I, and of course balance the numerator as well. Okay, so now your numerator, 3 times I is 3i. The denominator, I times I, is I squared. But remember, I squared is really -1. So now that's really your answer. And so it's pretty easy when you have just an I, of course, in the denominator. What if you have more than that? Okay, so I will remind you about conjugates. First, just basic non-complex conjugates. If you have like A plus B, its conjugate is A minus B. And the point of a conjugate is when you multiply a binomial times its conjugate, the outer and inners cancel out, right? So in that case, I'd have A squared minus B squared. Well, same with complex conjugates. If I take A plus BI times A minus BI, well, what's going to happen, and you can FOIL that if you want to see it, A times A is A squared, A times -BI, positive A times BI, those are going to cancel, right? And then my outer negative B squared, I squared, but what is I squared? It's really -1. So now I'm left with A squared plus b squared, and I have no imaginary parts after multiplying. So when you multiply complex conjugates, you eliminate the i's. So that said, if you look at this example, well, first and foremost, note that you're adding these together. So if you recall from a couple lessons ago, when you add fractions, you need a common denominator. Well, that means to make these denominators common, they both need the opposite binomial. So this one is going to need to be multiplied by 1 minus 2i, and I'll balance the numerator as well. The second part is going to need a 1 plus 2i, balance the numerator as well, right? So this gets very multi-step. So let me rewrite that. So my first numerator, if I distribute this through, I have 3 minus 6i plus 3 plus 6i. And then my denominator is 1 minus 2i times 1 plus 2i, right? Let's see, I didn't miss anything. So the 6 i's in the numerator cancel out. So this is really 6 over. And then what are you going to do with the denominator? This one worked out nicely that they just happen to be conjugates. But remember, you can't have i's in the denominator. So good news is these are already conjugates of one another. So if I FOIL those out, the i's should cancel. Right? So if I FOIL, I get 1 plus 2i minus 2i, and then minus 4i squared. It doesn't really look like an I, sorry. Minus 4i squared. So these cancel. This is really a plus 4, and 1 plus 4 is 5. And so this is really just a big 1 1/5. Okay, so there you kind of have some division questions. If you solve, I'm going to not necessarily go into great detail with this because I know you're confident, right, solving quadratics, but when you solve quadratics with imaginary solutions, the solving process doesn't change. So just to remind you, in example 16, you can't factor that because it's the sum of perfect squares. But if I subtract the 25 over, divide by 16, and then square root both sides, lucky for me, I can square root 25 and 16, but because it's a negative inside the radical, it's going to be a plus or minus. Don't forget plus or minus when you square root. And then, oops, maybe I'll rewrite that. So square root of 25 is 5, square root of 16 is 4, and then attach the I on, right? Okay, same with the example 17. Try to factor that if you want, you can. It doesn't factor. I can't isolate the x squared because there's an x in there, so I'm gonna have to complete the square or use the quadratic formula, and I'm gonna use quadratic formula. Okay, so x equals opposite of b plus or minus the square root of b squared minus 4 times a times c, 4 times 3 times 4. So 4 times 3, 12, 12 times 4 is 48. All over 2a, 2 times 3 is 6. That's okay, follow the, you should be okay with the quadratic, right? And then 4 minus 48 is negative 44. Over 6. And then simplifying that radical. Well, let's see. Square root of 44, that's the square root of negative 4 times the square root of 11, right? So this is going to be 2 plus or minus, square root of 4 is 2i, square root of 11, all over 6. And then don't forget, when you have a quadratic, you're dividing both of these by 6. So it's really 1 plus or minus 1i over 3. 2/3, 2 6, 2 6, 1/3, right? So stuff you know, and again, you could complete the square if you prefer. I just kind of was going through the quadratic formula more so. Okay, I'm going to go backwards then to the ones I skipped here. The patterns of imaginary numbers. I'm going to go through this kind of quickly, but you know I is I, right? So I to the first is I. We know I squared is -1. I cubed, well, if basically I cubed is another I multiplied to the I squared. So if I multiply an I here, I'm to -I. I to the fourth, multiply another I, all right? So I times I is I squared, which is a -1, so +1. I mean, you could keep going, right? Just keep multiplying by I and the pattern continues. Well, if I do that, I will erase these. Then I to the fifth is going to go back to I, so notice these are the same. I to the sixth is -1. I to the seventh is -I, and I to the eighth is 1. And it just keeps repeating. So every power 4 repeats the pattern of I, -1, -I, 1. And I'll erase these again so you can kind of see that better. So I to the 12th is 1, I to the 16th is 1, I to the 20th is 1, I to the 24th, you get the idea, right? So you could lay them all out if you really want, or because every 4th power repeats it, then when I go to I to the 23rd, rather than laying out that pattern all the way to 23, I'm just going to take 23 and I'm going to divide it by 4. And whatever the remainder is tells me in the first 4 where I fall. So if the remainder is, well, let's actually divide this out, so you can't really tell that's a 4. Okay, so 4 goes into 23 5 times, and my remainder is 3. That is critical. This tells me I'm going to go to the third one in the pattern. So that means this is equivalent to -I, because -I is the third one in the power, right? Same thing with I to the 302nd. Okay, so 302 divided by 4, since there's 4 in the pattern. So 4 goes into 37 times, 4 goes into 22 5 times, and my remainder is 2. Okay, so I'm going to go to the second one in the pattern, which is I squared, which is equivalent to -1. So this is equivalent to -1. So there you have it. Everything you wanted to be reminded about with complex numbers. Enjoy.